Okay, so I think we can start now. Well, I had some administrative announcements, but probably I stopped the lecture at a very wrong place. Like so, like we don't want to lose the continuity, so we'll have the announcements in the end. Okay, so let's continue where we left. So we are looking at dimensionality reduction, and specifically we are looking at how can I take my, I don't know, d-dimensional data and project it to just one dimension such that it has maximum variance, as much variance as possible, right? So now that is exactly defined by this particular goal. Okay, so I'm going to rewrite this goal in the next page. Okay, so the goal is to maximize the variance in the projected data, which is P transpose SP, right? Such that norm of the P is equal to 1. Okay, now this is actually equivalent to maximize P transpose SP divided by P transpose P such that P is not equal to 0. Okay, now here is where like one of your readings is going to be useful. So we're going to take this matrix S, which is the covariance matrix, right? And consider the spectral decomposition of this matrix. So now the spectral decomposition of this matrix is given by Q lambda Q transpose, okay, where lambda is, I think it is lambda, so is the spectral, sorry, this is called lambda. Lambda is basically a diagonal matrix where the diagonal values are the eigenvalues of this matrix S. Okay, lambda 1, lambda 2, and so on. Okay, and the Q is the matrix which has all the corresponding eigenvectors, right? So it's a matrix with orthonormal row vectors. Okay, and these are basically the eigenvectors. Okay, so this matrix is orthonormal, and hence Q transpose Q, or maybe depending on how you use it, like so Q transpose is equal to I. It's an identity matrix. Okay, so we are going to use these two information in our solution. So I'm going to just replace this as max P transpose Q lambda Q transpose P divided by, I'm going to add Q transpose in between this. Okay, so P transpose Q transpose P, because Q transpose is equal to an identity matrix, like similar to 1, right? So the max such that P is not equal to 0. Okay, so now we are going to assume that Y is equal to Q transpose P. Okay, so using this, I'm going to rewrite this again. So max P not equal to 0, Y transpose lambda Y divided by Y transpose Y. Is that clear? Okay. So now I know that the matrix in between is a diagonal matrix, right? So it has values lambda 1, lambda 2, lambda 3, and so on, right? And Y is a vector, d-dimensional vector, right? Okay. So I'm going to write this as max P not, okay, sorry. So this has to be Y. Okay, so Y not equal to 0. Lambda 1 times Y1 square up to lambda D times YD square. I have just expanded the term in the numerator. Similarly, you can expand the term in the denominator. It becomes Y1 square plus YD square. Okay, so we are going to consider lambda 1 to lambda D such that they are all sorted based on their value. Okay, so these are all the eigenvalues corresponding to the eigenvectors U1 to UD. Fine. Okay, so now I can actually decompose these terms. So this becomes max Y not equal to 0 lambda 1 times y1 square divided by summation over I ya square plus like every term like lambda d times yd square divided by summation over I y square. Okay. So there's a question about q transpose p. Sorry, that's not an assumption. Maybe that was a wrong word usage. So I'm just transform like this is just like a simple transform. Like so I am rephrasing q transpose p as y. So the y I'm just introducing y to club them together. It's a substitution. Yeah, substitution is the right one. Okay. Okay. So now I have this function that I want to maximize, right? So you can see that this terms that we have, right? Like, so these are like values that will sum up to 1. So you have a convex combination of lambda 1 to lambda d, okay? And if you want to maximize like a convex combination of bunch of scalars, right? Like, so in this case, assuming that they are positive, like it's essentially the maximum value of those scalars. So this is basically upper bounded by lambda 1. Okay. So now this term is upper bounded by lambda 1, where the equality equal to lambda 1 is attained when y is equal to E1. E1 is a identity vector, or like, I'm not sure if that is the right word, but it's like a vector like this. E2 is like an I vector with just the second entry to be 1 and so on. Okay. So now when y is equal to E1, Z is given by QE1, which is equal to U1. Okay. So where U1 is the first eigenvector of S. Okay, so what did we do here? So we were interested in maximizing the projected variance, and our derivation tells us that the variance can be maximized. Like, let's say you can choose only one direction and you want to maximize the variance, then the best direction to choose is the first eigenvector of the covariance matrix. Okay, so we're going to call this direction as the principal component. Okay, so the first principal component is given by the first eigenvector of covariance of X. Okay, now similarly, if you want to find two directions which captures almost all the variance, then you could choose the first two eigenvectors, then the first three eigenvectors, and so on. Okay, so for example, so now we have an algorithm. So if you want to find the k-dimensional subspace, okay, that captures maximum variance, then you just pick top k eigenvectors of the covariance of X. Okay, now this algorithm is known as principal component analysis, or PCA. Okay, so let me summarize the algorithm. So here's the procedure if you want to implement PCA. So basically, you will first compute the mean, mu, and the covariance matrix, yes, of the data. Okay, then you will compute the top k eigenvectors u1 to uk of S. Okay, so then you would project X to P transpose X, okay, where P transpose is basically a K cross D matrix whose rows are given by U1 to UK. You pick the top K eigenvectors, you put them together, that is your projection matrix. Now you can project your data into a low dimensional subspace. Okay, is that clear? Okay, so I think that concludes PCA. Maybe I will take a couple of questions before we proceed. Any questions, hand raisers, chat? Okay, Gabriel.
Hi, can you hear me?
Yeah.
Yes, I was wondering, I've read a bit about PCA, and in practice, people seem to be using the singular value decomposition instead of doing what you just wrote, but is there like an advantage to do a SVD instead of projecting with P transpose? Or
Well, I think technically they are same, right? Like, so I have to think a bit about the computational benefits. But in some sense, like even here, like what you're doing is like you like you're okay. Well, yeah, you're doing eigenvalue decomposition here, right? So now what exactly is your question then?
I'm just wondering because I've seen that sometimes, like in order to do PCA, people use the singular value decomposition, and then they use the U matrix that you obtain to then get the principal or to get directly the projections you did. But I assume maybe like
Okay, but that is exactly what we are doing here too. Like all we are doing is like you first compute the covariance matrix, and then you do an eigenvalue decomposition of this covariance matrix, and you take the U matrix.
okay, so the SVD would do exactly what we're doing, but like with a single call to a function. And,
Yes, yes.
okay.
But I need to think a bit more about the computational advantages of one versus the rest. So maybe I will get back to you on that like a bit later. Okay. And there is a question in the chat. How does this approach reduce the dimensionality? Well, like you take a 10-dimensional data and you could reduce it to 1D, 2D, right? Like so you are reducing the dimensionality by like considering like the first few eigenvectors. Are the eigenvalues ordered by their absolute value or their raw value? Well, that is a good question. Maybe I will check and answer in the end of this lecture. I'm not able to like think immediately. Okay, wouldn't SVD be stronger since eigen decomposition is strictly F or for square matrix? Well, that is true. So but remember that your covariance matrix is always a square matrix. There is another question. How do you choose how many eigenvectors you want to use? Well, like, so that is exactly what I was describing probably during the break. So like now you could consider like what fraction of variance you want to capture, and you could define an iterative procedure where you just consider the first eigenvector, see how much variance you're capturing, add the second, add the third. You can have a threshold. Like when the threshold is achieved, like you could just stop. Okay, so maybe let's continue. Okay, so now before we so far what we have seen is like, so we wanted to do dimensionality reduction, and we are doing that by the algorithm PCA, right? So since we discussed a lot about classification in the last few lectures, like one obvious question that we might be interested in is like, can we actually use PCA dimensions for classification? Right? So can I use these PCA dimensions to come up with a classifier? Okay, to answer this question, let's actually take some example data point. Okay, so let's say I have a bunch of crosses and a bunch of circles like this. Okay, so now what would be the first principal component for this data? So maybe we can do a poll. Okay, so I will give you two options. So this is option A and this is option B. Okay, so let's do a quick poll. 1 second. So we want A versus B. What do you think is the principal component, the first principal component for this data? Remember, I will stop the poll in 15 seconds, so you have to be fast. Okay, let's stop. Okay, so 60% of you think option A is right, and there's 4% who thinks option B is right. Well, I think in this case, it's actually A. So like one way to find the most important, the primary principal component is like, which is the direction in which the data is varying a lot, right? So probably this length is more than this length, I guess. So let's go with A, okay? So now this A is the first principal component. Now what happens when I project all my data to the first principal component? Okay, there's a question, how is A varying more than B? So that's because of my drawing skills. So if I put something like this, let's say, now you can clearly see that this length, this direction has more variance. So maybe it was my drawing mistake. Okay. Okay, so yeah, so now what happens if I project all my data to this direction A, right? So let me see if I can remove this thing. Okay, so what happens if I project all my data to this direction A? So you can see that as you project everything, these data points, which are actually linearly separable, has become completely mixed and collapsed, right, to the same region, right? So in some sense, it is not a good idea to pick the first principal component and project the data into it, like if you want to do classification. Okay, so now the next question is, okay, is there any way in which we could actually do this dimensionality reduction in such a way that the classes are separated so that I can easily do classification? Okay, so we're going to look at a better solution. Okay, like we are going to, instead of asking for a projection which maximizes the variance, okay, so we are going to find the projection that maximizes the class separation. Is that clear? So now consider a two-class problem in which, let's say I have n1 points of class C1 and n2 points of class C2. Okay. Now, what would be the mean for these two classes? So the mean vector of C1 and C2 are given by, the mean for the class 1 is simply the average of all the data points in class 1, right? So summation n belonging to C1 x power n 1 over n1, right? Similarly, m2 is given by 1 over n2 summation n belonging to C2 x power n. right? So now the problem is you choose W so as to maximize W transpose M2 minus W transpose M1. Okay. So let me just write it as an objective function that we want. Let's say we want to maximize W transpose M2 minus W transpose M1. Now we have the same issue as the PCA. So if we just try to maximize this function without any constraints on W, then you could just keep increasing the magnitude of W, right? So we have a constraint which is subject to W transpose W is equal to 1, or now is 1. Okay, so now this is the new objective function. Okay, so for a minute, let's compare this with whatever we had for PCA, right? So in the case of PCA, let me see if I can go back to the PCA. Yeah, in the case of PCA, I was interested in maximizing the covariance, right, like of the data, of the projected data, such that P is equal to 1, right? On the other hand, my maximization function here is to maximize the distance between the projected means of the classes. Okay, so in some sense, PCA is, okay, so in some sense, PCA is an unsupervised algorithm. Why is that the case? It's unsupervised because it doesn't use the class labels. It just considers X. There's no place in PCA where we used Y, right? On the other hand, for this particular optimization function, okay, let's just call this, for the sake of naming it, like let's just call it M1, okay? For M1, it's a supervised algorithm. Why? Because to compute M1 and M2, you need the class label. Okay, so maybe my bad, I have two M1 here. So let's just call this as algorithm 1. Okay, so algorithm 1 is supervised algorithm simply because we are using, okay, so that's fine. So now let's see how to solve this function. So it's a constraint optimization problem, and you have already seen how to solve constraint optimizations using Lagrangian in your reading, right? So we are going to look at the Lagrangian formulation for this problem, which is basically W transpose M2 minus W transpose M1. Instead of having the constraint separately, we are going to add it to the objective function as plus lambda times W transpose W minus 1. Okay, we have seen this before, like when we discussed about L1 and L2 regularization, right? Like, so in the case of L1 and L2 regularization, like so this looks like an extra regularizer term, right? Like, so when we add an extra regularization, we also saw the corresponding constraint optimization problem. So we are doing the opposite of that here. Okay, so now you can differentiate this, set it to 0, you're going to get your solution. Okay, so dou L by dou W is given by, maybe one more step, I could just write this as W transpose of M2 minus M1, right? So when you differentiate with respect to W, you get M2 plus M1 plus 2 lambda W is equal to 0. Okay, so now I could just rework, like put these things here, like transfer things between left and right, and I would get W is equal to minus 1 by 2 lambda M2 minus M1. Okay, and we care more about the direction than the magnitude. So all we need is the direction, right? So W is proportional to M2 minus M1. Okay, so what does this mean? So the solution to this maximization problem is actually very intuitive. It says, if you want to maximize the distance between M1 and M2, then you basically consider the line which is connecting M1 and M2. Okay, so like let's look at how this works in, let's say, in this example. So I have blue, let's say class 1, and red as class 2. Okay, now the mean for the class 1 is given by this particular plus, and the mean for class red is given by this particular plus. Okay, so now the equation for m2 minus m1 tells you that it's a line between m1 and m2, right? So you just connect these two, right? So that is the direction. So now you project all the data points in that direction. You can see that like the separation is minimal, right? So remember that for the same data set, if you want to project to the principal component, the principal component for this data set is this, right? You project to this red line, everything collapses. On the other hand, if you use algorithm 1 and you project it to the line given by the algorithm 1, this is the projection. You can see that there's a separation. It is still not perfect, right? Like you can see some misclassifications, but this supervised algorithm is much, much better than the like naive way of using PCA for classification. Is that clear? Okay, so maybe I will take one or two questions before we move to the next solution. Any questions, hand raise? Can we say the optimum is orthogonal to PCA? No, you cannot say that. You can come up with examples where that is not true. Otherwise, it's a simple algorithm, right? Like you just do PCA and then take the orthogonal. So it will not be the case. Okay, so does this new algorithm have a name? Probably, but I am not sure about the name of this algorithm, like simply because this is just a intermediate algorithm before we see another well-known named algorithm. But maybe I will look for like what is the actual name for this algorithm. But for now, let's just call it alg1, even though it's not very interesting name. Okay, so let's continue. So as you can see, even with this algorithm 1, there is some misclassification, right? They can actually do something better than this, right? So the problem here is the classes are actually well separated in the original data, right? Like so when I project it to a low dimension, I want the performance to be better. I don't want the performance to go bad, right? Like so why is this happening? So why is there a considerable overlap even in the projected space? Like when I'm trying to explicitly maximize the gap between the means, right? It's simply because we are just focusing on the mean and not on the covariance of the class distribution, okay? And in this case, it happens that this particular data set it has strongly non-diagonal covariance of class distribution, okay? As someone rightly pointed out in the beginning, variance is the most important thing that you should care about, not the mean, right? So can we do something better than this? So there is a better solution, in fact, a named solution by Fischer. Okay, so this is the solution proposed by Fischer, probably in 1930s or 50s. I'm not sure. Probably in 30s. I'm not sure. Okay. So the idea is this. So Fischer said you maximize a function, okay, that will give a large separation between the projected class means up to this point is what algorithm 1 is, right? But he adds an extra constraint. So he says, while also give a small variance within each class, thereby minimizing the class overlap. So he says it is not if you just maximize the distance between the means. At the same time, also try to reduce the variance within the class. Okay, so we don't need the variance within the class, right? Like we want to classify all the examples of one class to be the same class, right? Like so it's okay if you shrink the variance of the specific class. Okay, so now that is his formulation, like his idea. Now we need to rewrite this mathematically, right? So to do that, let us consider the within class variance. Within class variance of the transform data. So once I transform the data, what is the variance within one specific class? Let's take class CK. Okay, for class CK, I have the variance, let's call it SK square, which is basically summation over n belonging to CK, W transpose XN minus W transpose MK. This is just a definition of variance, but only for class CK, right? Now we have two classes. So the total within class variance is given by S1 square plus S2 square. Okay. Okay. So now we have the Fischer criterion, which is what we are trying to maximize. Okay. So we want to maximize W transpose M2 minus W transpose M1 the whole square. This is same as the previous objective function, but divided by S1 square plus S2 square. So I want to maximize this term. So the denominator is minimized. So you're minimizing S1 square and S2 square while maximizing the distance between the mean of these two data points. Is that clear? Okay, so now we need to consider these two terms and simplify them so that like it's easy for us to do the maximization process. So let's take the numerator, W transpose M2 minus W transpose M1, the whole square, right? So this is given by W transpose M2 minus M1, the whole square. Now we have done this before, so I can write this as W transpose M2 minus M1, M2 minus M1 transpose W, right? Now this term in between is equivalent to the variance, but this is the between class covariance matrix. Okay, so now this is given by W transpose SBW. Okay, now this is the between class covariance. Okay, now let's consider the unit, which is, maybe let me move to a next node. Let's consider the denominator, which is S1 square plus S2 square, right? So now this is given by, I'm just going to expand, summation over n belonging to C1, W transpose Xn minus M1, the whole square. So this is for class 1, plus similarly summation n belonging to C2, W transpose Xk minus M2, the whole square. Okay, so now this is given by summation over n belonging to C1, W transpose Xn minus M1. I'm just expanding this, Xn minus M1 transpose W. So this is the first term. I just expanded it internally. Plus the second term is given by summation n belonging to C2, W transpose Xk minus M2, Xk minus M2 transpose W. That's right. Okay. So now I'm going to write the whole thing as W transpose SWW, where SW is given by just these terms. Okay, so it's given by summation over n belonging to C1, Xn minus M1, Xn minus M1 transpose, plus summation over n belonging to C2, Xk minus M2, Xk minus M2 transpose. Okay, now let's just call this as 2. So the first numerator is, the numerator is simplified like this. and the denominator is simplified like this, right? So now I can actually rewrite my objective function as we are interested in maximizing W transpose is BW divided by W transpose is WW. Okay. Now this is easy. You differentiate this, set it to 0, you have the solution. Okay. So now you differentiate this. So this is U by V, right? Okay, maybe let me rewrite this in the next page. Okay, this is my function. You differentiate it, set it to 0. So now to differentiate, this is U by V, so it's U dV minus V du. So it's U dV, differentiate the denominator. You would get SWW, right? Minus V du, right? So SBW is equal to 0, right? So now this becomes W transpose BW, SWW is equal to W transpose SWW, SPW, right? So okay, let's call this a C star. So we do not care about the magnitude of W, right? So all we care about is the direction of W. So let's just cancel these terms, which are just the magnitude, okay? Now we have SWW is equal to SBW, okay? Now we know that SB is given by M2 minus M1, M2 minus M1 transpose, right? Which means SBW is always in the direction of M2 minus M1, right? So one way to write the whole thing is as SW is going to be in the direction of M minus M1, and W is given by SW inverse M2 minus M1. Okay, so now this is the solution for the maximization problem that we had. Okay, so now what does this tell us? So this tells us that W is proportional to M2 minus M1, which is same as the algorithm 1 solution, right? But it adds an extra term, which is basically the inverse of the within class variance, right? Or in other words, if the within class covariance is isotropic, then SW is proportional to the unit matrix, and this solution like falls back to the previous solution that we had. Okay, so especially when this term is identity, then this is the same solution as the previous solution, right? So this specific objective function and its solution, it has name because of Fischer. So this is known as Fischer's linear discriminant analysis, or in other words, LDA. Okay, so now let's look at the LDA solution for the same problem. So this is the same problem which was linearly separable in the original space, right? So just to give you a reminder, if I do PCA, okay, now my PCA line would be something like this, approximately. Okay, now remember the algorithm one line would be something connecting these two. This is my algorithm. I should have a name for algorithm one. It's algorithm one solution, right? Now, on the other hand, if you look at the LDA solution, which is given by this green line, you see that you project the data into this green line, you actually have perfect separation. Okay, is that clear? So this is known as Fischer's linear discriminant analysis. However, note that the name Fischer's linear discriminant is often confusing because like what we have seen here in this algorithm is not a discriminant. Okay, so what we have seen is just a direction to project, right? This is just a projection. Like, so now you need to come up with a classifier which is going to divide these data in this projected space. So that classifier is not given by Fisher's LDA. So in some sense, it is not a discriminant function. It is just a projection. Like, it is just a direction for projection. Okay. So now the next obvious question is like, how can we come up with a classifier by using Fisher's LDA? But before that, maybe I'll take a couple of questions from the chat. Okay, so there's actually, I think most of them are answered. So is algorithm one the special of Fisher's algorithm? Yes. So when you are, especially when you're SW matrix, right? So yeah, when this SW matrix is isotropic, sorry, when your within class covariance is isotropic, then this SW is proportional to unit matrix. In that case, like, it's just the same algorithm. Okay. Okay, so oh yeah, so oh, yeah, yes, okay, so that is right. So probably I should just call this as they are proportional. Okay, so I think there is some confusion in how I was very loose in this part. That's simply because we only care about the direction, we don't care about the magnitude. So we just remove anything which is for the magnitude and just find the direction. Okay, so maybe before we conclude, like, so we also want to ask a question: how can I use this LDA to do classification, right? So let's go back to this picture. So you can see that once you project it to the base, right? Like, so the histogram space that you see here, we want to come up with a decision boundary such that the data is like the data to the left of the decision boundary is, let's say, blue, and to the right is red, right? So how can we do that? So we can do that by coming up with very simple heuristics based algorithm on the top of this, which is basically the idea of finding a threshold theta. Okay, so you keep varying this theta and see for which theta. So basically, first you come up with the theta and then say W transpose X greater than or equal to theta means class 1, W transpose X less than theta means class 2. Okay. Now you try different values of theta and look at the training error, and whichever theta gives you the minimum training error is the theta. For example, to give you an example here, I could consider this as the theta first. Okay. Now, okay, I need a better color. Let's say this is the theta. Okay. Now, if I consider this as the theta, then there is some misclassification here, right? Like, on the other hand, if I consider this green line as the theta, there's a perfect classification. So you could just do that by using the training error. And then, like, once you have that, now combining the projection layer plus the classifier, you have a classification algorithm by using Fisher's linear discriminant analysis. Okay. So I think that I don't want to start something with the given 5 minutes. So probably we will start the next topic in the next lecture. But this actually gives me the time for the few feedback announcements that I wanted to talk about. So again, once again, thank you for people who are giving your feedback in anonymous Google Forms. I'm actually reading them every day. So I wanted to answer some of your questions. So someone mentioned that, like, you really liked the "you must know" section in the end of the chapters. Well, I really want to write it for every chapter. Like, it is just that I'm writing these notes in, like, the day before the lecture, and like I just rushed to put it online so that you have the notes at least few hours before the class. But I will update all the lecture notes with a "you must know" section probably by this week. So So I did not forget, you must know. It's just that I did not have time to do that. And there are some other feedback. So regarding the assignment, I wanted to clarify something. So there were some questions in Piazza about, okay, so how to do feature selection using Ridge, and it was not taught in the class. I want to again highlight the fact that assignments are complementary to the lectures. So these assignments are not like, basically like these are not assignments where I ask you to just implement what is taught in the class. So assignments are also supposed to make you think and come up with your own algorithms and own solutions and some modifications to the existing algorithms, right? So the feature selection using Ridge is just a simple example for that, right? Like, so like, you know how to do Ridge. All that the question asks you is, how can you use this to do feature selection, right? So similarly, like to give another example from today's lecture, like I could have just stopped the lecture with LDA and I could ask you, okay, how can you implement, how can you utilize this LDA algorithm to do, come up with a classifier, right? So now this part, like where I told you that, okay, you have to come up with the theta and find the theta using training error. Like, so I might expect you to do it by yourself. Like in some sense, like I want you to come up with like modifications to the existing algorithms and also to come up with your own algorithm. So that is also the scope of the assignment. So assignments are not just to simply implement like what is taught in the class. I thought I made it clear in the beginning, but I'm just making it clear again, so that there's no confusion that there are questions in assignments which are not taught in class. So you can expect such questions. Like, so these questions are to help you think and come up with solutions. Okay, so then there's also, is there any other comment? Well, if you have any other feedback or comment, like we have time, you could post it in the chat now. Two more comments. Like, so one is, as you all know, my office hours is right after the Monday lecture. And it is in the same video call. I just stay in this call, right? Like, so 2:45 to 3:45. But most often, all the people drop around 3:15, and so maybe as a strategy, like I would wait till 3:30. So if there's no one up to 3:30, I will disconnect the call. So this is just to make sure, like try to come for the office hours within the first 45 minutes, so that there's enough time in the last 15 minutes to answer the questions who are already in the office hours. So there was also another comment that the course is very mathematical. So I would like to remind the course objective again. So as mentioned in the beginning, the aim of the course is not just to teach how to use ML algorithms, how to tune your hyperparameters. It's more about it's more about explaining why some algorithms work, how do they work, and like when these algorithms work, right? So to understand more about these algorithms, you have to know how these algorithms work. And that involves math, right? Like, so machine learning is in some sense applied statistics. So you should expect a lot of math. But if there is anything if there is any non-trivial like background that I expect from you, I give it in the reading. Otherwise, most of the assumptions that we make for this course are, you should know how to differentiate, you should know how to compute expectations and variance, and probably you should know how to play with matrices, right? So these are the very basic assumptions that we make. And if you have done a probability or linear algebra course, you should have all these skills. Will we need to solve maths in exams? So I will not expect you to remember a derivation and do that in the exam, okay? So, but what I would expect is that you know how to differentiate things. So if there's one math skill that you should or you must have, that I would test is like, you should know how to differentiate things. And the course is taught in such a way that everything else can be done by you from scratch, from first principles in the exam. So if I ask anything math in the exam, it is not going to be based on remembering things. So for example, let's say there's a question which has to do with like the PDF of Gaussian distribution. I would just give the PDF of Gaussian distribution. I'm not going to ask you to remember formulas. So, but you should know the basic things. For example, you should know how to differentiate. And most probably you should remember the linear regression solution by heart because we have seen it, I don't know, 5 or 6 times in 7 lectures. So these are the only minimal expectations that I have for the math. But as much as we do math in the class, you have to like remember that like the most important thing is the intuitions that you develop through this math. So focus on that. Okay, the difference between the course and math. Okay, again, to highlight, this is not a math course. Like, so this is about understanding why machine learning works and like developing these algorithms from first principles. And you can see that the tone of both the courses should be completely different because like we do care a lot about applications. Like you are doing a lot of applications in your assignments. You are doing a lot of applications in your competition that you're going to do and so on. And you're learning all the machine learning packages.
I think if I can add, Sarath, I think the math requirements are pretty well resumed also in assignment 0. So if you really understand assignment 0, then you should know, you know, what is required in terms of math.
Yeah, but again, like I just keep repeating this, like don't worry if you don't get a part of math in the class because they're using math as a medium to understand the algorithm. So the ultimate objective for like the lecture is like getting the intuitions right. You could always go back and work on the math. Okay, so maybe I'll just answer one question before I stop the recording and go to the office hours. Do we know if the final exam is going to be replaced by an assignment or not? I'm still in discussion with the university. So technically I need approval from the university to change the evaluation plan. So as soon as I have some information from the university, I will let you guys know. Okay, I'm going to stop the recording now, and then I'll take more questions.